Alright, hello class. In this video we're going to be sort of answering that question that we ended with last time. At least the concept that was introduced last time, to where we're going to be looking at line integrals over vector fields. And how you can think about this is if our vector field represents forces, say current in a river, and we're a boat traveling along a path in that river, at each individual point we're going to have a vector in that field applied to that point in the path. And for each one of these we're going to have, say, changing along that path more than likely. Okay, so the current will be pushing the boat around in different directions at different magnitudes at different points along the path. So the question then becomes, how do we calculate, say, the work over or the amount of force or what have you along this path applied by this vector field? Alright, so there are two types of line integrals over a vector field, and the first one we're going to talk about, and the main one, is what we call circulation, and this is actually equivalent to work. Okay, and here's how it goes. Imagine we have a path moving through a vector field. So let's call the path C, and say it's represented in this way. At each point along C, we have a tangent vector, the unit tangent vector to be precise. Okay. Now, if C is represented by the vector valued function, say r of t, which is likely, considering that this is an oriented path, therefore there should be some sort of r of t. This t, capital T, is going to be r prime, divided by its magnitude, right? It's the unit tangent vector. Okay. Also, so basically the t gives us the direction of travel at each point along the path. Okay, then also at each point the vector field F will be affecting our travel in some way. It might be pushing straight across, it might be pushing along with us, right? It might be pushing in this way, or we might have situations like this where we're traveling this way, but the vector field is always pointing away, right? Pushing against us. All right? So, remember, right, that F dot T measures the amount of force F gives to T in its original direction of travel. Okay, so at each point, F dot T is going to tell us how much F is pushing along the direction of our path. Okay, so if we want to add or get an idea of what's happening along the entire path, it becomes an integration. So the total amount of push that the vector field F enforces on C can be given by the line integral. I usually write it as like the circulation over C. Circ C is the integral over C, okay, of F dot T ds. Okay, and S S is basically the length of the curve. So where S is the arc length of the curve. Now I don't want to spend too much time on arc length parameterization and all that kind of stuff because I don't find it that helpful as far as like how we are actually going to solve most of the problems here. So what I want to focus on is how we usually think about this, and how we usually think about this is in terms of R of t, and so that at each point along here is a different t value, right? This might be t equals 0, this might be t equals 1, t equals 2, and so on and so forth. Okay, so I'm instead going to look at how we deal with this in terms of time. Okay, so I'm going to parameterize it in terms of time. However, if you remember the arc length of a curve, so the arc length, if you remember, was ended up being the magnitude of r prime of t dt. So it turns out that basically what's happening is that ds ends up being the magnitude of r prime of t dt. Okay, that's, I don't want to get too in the weeds there. What I do want to show is how you can think about this in terms of time. All right, so let's let this be our path C. It's oriented in this way. And it has a parameterization given by a vector valued function. So C is an oriented path, right, given by the vector valued function R of t. Okay, so now I'm going to split this up into pieces. They might not be the same size. Okay, they might be the same length, they might not, but I'm going to split this up into delta t's, right, into smallish delta t's, and then we're going to zoom in on one of these, and I'm going to split this up into a very small delta t. Okay, so let's split this up into, say, a small delta t. All right, so this might be r, this point here might end up being r of, let's say, t sub k, and this point here would end up being r sub t sub k plus 1, but it would also specifically be r sub, r sub t sub k plus delta t. Okay, now what we can do here is take a look at this. Okay, we can take a look at the vector we get from these 2 points. So let's call this vector d sub k. Okay, and then I'm going to look at the force vector made from the vector field at this point. This would be x sub t sub k and y sub t sub k. Or this would actually be f evaluated at r. That's often what I call this. That's not the greatest notation. Some people would yell at me for that, but I think it's actually kind of nice, because what I'm doing is I'm plugging this point in to f. So whatever this x sub k, y sub k is, I'm plugging that in. But we get that x sub k, y sub k from r. Okay, so yes, it's an abusive notation. However, in this particular chapter, you're going to see a ton of abusive notation, just because if we don't abuse notation a little bit here, we are going to end up with horrible just nasty formulas, all right, unreadable math. Okay, so what we're going to do in this little thing is I'm going to assume that this is small enough that approximately this d is approximately the full distance traveled here for this particular arc length. So if this is, say, delta s, we'll assume we're going to assume that this little vector I just created is a displacement from r sub t, or from t sub k to t sub k plus 1. We can make that assumption because we're going to get delta t small enough to where they're eventually going to be very similar. In fact, if we zoomed in even closer to here, eventually you'll get to the point where it just looks like a line, right? And when you make a vector on top of it, it's going to essentially be the same thing. This is exaggerated so you can see more what's going on, but this is essentially what we're doing. Okay, now this vector, well, essentially we are creating a delta x sub k and a delta y sub k. Okay, so our d sub k is the vector delta x sub k comma delta y sub k. Well, why am I doing this? Well, remember the work that F applies along a displacement d, right? So remember the work applied by a force F along a displacement d is F dot d. Okay, well, F dot d, well, in this case, so the work along this path here, which we'll call W sub k, so the work along D sub k, okay, W sub k, is F of, let's just say it's x sub k, y sub k, dotted with D sub k. All right. Now, that means the total work, so there's the work, say, along this part of C, right? So then the total work along C, okay, it's going to be approximately, well, we're going to sum all these up. We'll take the sum of k going from, say, 1 to n of the vector field capital F of x sub k, y sub k. And we're going to dot it with d sub k. Well, remember, d sub k is a delta x, delta y. So this is a delta x sub k, delta y sub k. Okay, and we're going to do something we did similarly when it came to arc length, right? We're going to introduce a delta t under these. So we're going to get that this is the sum, k going from 1 to n, of f of x sub k, comma y sub k, okay, dotted with x, or delta x sub k over delta t, comma delta y sub k over delta t times delta t. So what we really did here is we introduced a delta t over delta t and then just brought this one inside. Okay, then if we take the number of pieces that we chop up, let n go to infinity, or we let delta t to go to 0, right? So the work will actually equal, and here it's when we take the limit as either n goes to infinity or delta t goes to 0, okay, this sum, remember, becomes now an integral. So we're going to get an integral of f, okay, of x of t, comma y of t, dot, well, this will become x prime of t, comma y prime of t, right? So if we take a delta x over delta t, as delta t goes to 0, that becomes the derivative, and then dt. Okay, and if I never said what my starting t was, but let's say t starts from a and goes to t equals b. Okay, so the integral is going to be over the entire t going from a to b. Okay, so I think a simpler way to write this would actually be the integral from a to b of capital F of r of t. And actually, I will drop the of t, so it's just going to be capital F of r dotted with r prime dt. Okay, and remember what the dot product does. All right, this will be the integral from a to b of, well, remember what f is. F is a vector field. Let's say it might be f comma g, right? And those are also in terms of x and y. But what the dot product is going to do is going to be f dot x prime plus g dot y prime dt. Okay, so sometimes, because of this, because of what this is saying, this is sometimes written like this. Line integrals are sometimes given like this. It will be the integral over c f dx plus g dy, because it's basically telling you how this works. Okay, what we end up with at the end. So let me consolidate this into something a little more formal. And I do want to say that there's more to this than what I've done to show you here. This is very hand-wavy. The truth of the matter is this module that we're spending on vector fields, you could actually take an entire class on just that. In fact, there is a class on that. Some places call it vector analysis. And it's an entire 3-hour course on just vector field calculus. Okay. All right. Okay, so consider the vector field capital F equals little f of xy comma little g of xy. Then the circulation of capital F over the path C measures how much of the vector field pushes along with C, right? i.e. it's the work of F along C. So is the vector field helping us along the path, or is it working against us? Okay. So if C is parameterized by this vector valued function r of t, let's say equals x of t comma y of t, then we get the following line integral. The circulation of F over C. This part's not necessary. I just like to write it sometimes. It's written in a lot of different forms. So it can be written like this: the integral over C. So that we're basically just saying we're integrating over C of capital F dot t ds. This can also be written as the integral over C of little f dx plus little g dy. Okay, and it's going to be this integral here in terms of t. If we can parameterize C in this way, it's going to be the integral from a to b. I don't think I gave t values here. Sorry, let me do that. All right, it'll be the integral from a to b of f of r dot r prime dt. Okay, so in other words, this is going to be the integral from a to b of little f with r plugged into it times x prime plus little g of r plugged into it times y prime dt. Now this one I don't use that much. I typically just work with this one, and that's typically enough. But this can be fairly funky to work with, so we will we will do some examples and hopefully it will clear things up for us. Okay, so to start with our first example here, let capital F be the vector field 2x, 2y, and let's find the circulation of capital F over the unit circle. Okay, all right, so remember the circulation is this line integral here. It's f dot t ds, but more specifically, it's the integral from a to b of f of r dot r prime dt. Okay, well, what that means is we need to find r, we need to find capital F of r, we need to find r prime. So the unit circle is our C, and we can parameterize that. Right, here's our path. We can parameterize that with this vector valued function. R of t is cosine t, comma sine t. And I didn't specify here, but we want to do this over the unit circle oriented counterclockwise. That's important because the direction we go in is extremely important here. Because if we go in the opposite direction, it's going to change whether the vector field is pushing against us or not. Right? So we're looking at the vector valued function cosine t sine t, where t is between 0 and 2 pi. Okay. So let's see here. We found our r. Perfect. Now we need to find f of r. So what I mean by f of r is f of cosine t sine t. In other words, this is capital F of xy is equal to 2x comma 2y. So what we're doing is we're putting cosine t in for x and sine t in for y. Okay, so instead of the vector 2x, 2y, we'll get the vector 2 cosine t, comma 2 sine t. Okay, while we're at it, let's find, so here's f of r, perfect. So we got that piece. Let's find r prime now. Well, r prime, we just take r and take its derivative. So cosine t sine t, we're going to get negative sine t, comma cosine t. Okay. Now, we don't have to do this before we set up the integral, but I like to. I like to go ahead and find f of r, and I dot it with r prime. Okay, so this is going to be 2 cosine t, comma 2 sine t, dotted with negative sine t, comma cosine t. And this is going to be interesting because when we take the dot product, we're going to get negative 2 cosine t sine t plus 2 sine t cosine t, and these guys cancel and leave us with 0. Okay, so that means our line integral f dot t ds is going to be now the integral from 0 to 2 pi of, well, 0 dt. Right? That's what this thing ends up being. Well, the integral of 0, definite integral of 0 is 0. Well, okay, what does this mean? Well, in this case, remember that this vector field, the 2x, 2y, this is what I call the explosion vector field. And if we were to look at this vector field and graph it, we would notice that at every point along this path, the vector field is perpendicular to the direction of travel. All right, I'm not drawing it super well, but at every point, right, F is perpendicular to T along C. Okay? Which means, well, that F dot T is going to be 0 at every point along C. And that's why we get 0 here for the line integral. This 0 circulation, right, means either F is perpendicular to C or that it's a balancing act, that F is with C just as much as it is against it. Okay? All right, so let's look at another example. Okay, let's look at the same vector field, but now we're looking at it over the line segment from 0, 0 to 1, 1. All right, so 0, 0 to 1, 1 is basically this. Okay, and if you remember, if this is our C, our R of T in this case, well, it's always, remember, we have to be careful about what direction we're going in. But in this case, it's always the initial value plus basically our delta x by delta t times t. All right, and we always set this up so that t is going between 0 and 1, and this is what I was talking about when we went over that lesson, was this is why, because we want the simplest limits for integration that we can possibly get. So this will be 0 plus 1 times t, and then 0 plus 1 times t. Okay, so it's basically just t comma t. All right, so we have that. Now let's remember what we're looking for. The circulation is the integral over C of f dot t ds, which is also the integral from a to b of f of r dot r prime dt. So we found the r, now we need to find f of r and r prime. So f of r, well, that's just going to be f of t comma t. So we're going to put t in for x and t in for y. So we're just going to get the vector 2t comma 2t. All right, so this one doesn't end up being all that bad. All right, now, all right, there's f of r, and then we need r prime. Well, r prime in this case will just be 1 comma 1. All right, so now when we set up this integral, it's going to be the integral from 0 to 1, and this is what I meant when I said we always do line segments this way just to simplify our lives. Okay, and so it will be 0 to 1, then let me go ahead and put it in this way, 2t comma 2t dot 1 comma 1 dt. All right, so we'll get an integral from 0 to 1 of 2t plus 2t dt. So it's the integral from 0 to 1 of 4t dt. So as I said, I often do this part up here beforehand, but it works either way. right? And now we just integrate. We've turned it into a Cal 1 problem. So the integral of 4t will just be 2t squared, and then we'll evaluate it from 0 to 1. So we'll just get 2. Okay, so what does this mean for us? Well, this vector field, if you remember, at the point 0, 0, well, we're just going to get 0. At 1, 1, we're going to get the vector 2, 2, right? And at the point 1 half, 1 half, right, here's the point 1 half, 1 half, we're going to get the vector 1, 1. So we'll get, say, this vector. So all the vectors along this line are pointing along the path. So if I look at a zoomed in version, okay, here's a zoomed in version, all the vectors along this path, and I'm going to make them a little smaller than they actually are here. They're all matching up with the path exactly, right? So here all vectors, all the f vectors push along the path C, so we end up with a positive number. All of these f dot t's are positive, right? So we end up with a positive circulation. Okay, since F pushes along or along with C. Okay, now if I were to go in the opposite order, right? If we went from, say, 1, 1 to 0, 0, we would see the opposite. Okay, so here's what we'd see if we went from 1, 1 to 0, 0. So here's why direction matters so much. Because if we did that, right, going from 1, 1 this way to 0, 0, well, now that completely changes our vector valued function, because remember it's an x naught plus delta x times t, comma y naught plus delta y times t. Well, here the x naught and y naught are now 1s, right? X naught is 1, and then how much does x change from 0 to 1? Negative 1. So it's 1 minus 1t, comma 1 minus 1t, or just 1 minus t, comma 1 minus t. Okay, and t going from 0 to 1. Okay, so there's our r. F of r, well, that's going to be f of, well, 1 minus t, comma 1 minus t. And again, that just means if our f is still 2x, comma 2y, we're just going to plug this in for x and this in for y. So 2 times 1 minus t, and then 2 times 1 minus t. Okay. All right, and then our r prime, right? We need that as well. R prime will just be negative 1, comma negative 1. And I'll go ahead and do it ahead of time here. F of r dotted with r prime. That's going to be this vector dotted with this vector, so it will be negative 2 times 1 minus t minus 2 times 1 minus t. All right, so it will be negative 4 times 1 minus t, or negative 4 plus 4t. All right, so when we set up our line integral over c, so notice this c is different. It's a different orientation. Even though the path is the same, remember that's a big deal. How we travel along that path is completely different. So our f dot t ds in this case will be the integral from 0 to 1 of negative 4 plus 4t dt. Okay, so we'll get negative 4t plus 2t squared from 0 to 1. And this is exactly why we set it up with limit 0 to 1, because it makes this integration so much easier. So it'll be negative 4 plus 2 minus 0, okay, which is negative 2. So we get the exact opposite here, because as we travel along this path, F is pushing against us the entire time. That gives us a negative circulation. Right, since F pushes against us the entire path. Okay? Let's look at another example. Okay, so let's find the circulation of vector field F equals negative y comma x over the two paths that we just did, cosine t, sine t, and t comma t. So this is the unit circle. And this is the line segment from 0, 0 to 1, 1. All right, so let's see what we get here. So for 1, we'll just call this whole thing 1. We already have our r. Okay, so we need to find our f of r, and specifically it's f of r1. So f is negative yx. So in this case, and this is where things can get really funky if you're not careful, we're putting cosine t in for x and sine t in for y. All right, so that means our vector field, which is negative y comma x, well, negative y will give us negative sine t, okay, and x will give us cosine t. Okay, something to be careful about when you do this. Right, then we need r1 prime. Well, r1 prime, if we look at r, it's going to be negative sine t comma cosine t. Well, it's the same thing. And once again, I forgot to give t values here. Sorry about that. I think I just get overexcited. All right, now, now we're going to take the dot product. Well, the dot product ends up, well, it's negative sine and negative sine, so you get negative sine times negative sine, so that's sine squared t, and then it's cosine times cosine, so we get cosine squared t, so we get 1. So we're just integrating over 1. So the line integral over c1 of f dot t ds is going to be, here let me write it out as an integral in terms of t. It will be the integral from 0 to 2 pi. In this case, 1 dt. Well, this just comes out to be 2 pi. Okay, well, if we remember, this was the rotation vector field. Right, so the rotation vector field along the unit circle, so here's our unit circle, but our rotation vector field behaved this way. Okay, so in this case, F pushes along the entire path C. All right, my audio cut out here, but I was just saying that if F is pushing along C the entire time, then that means we have a positive circulation. All right, so for path 2 here, we have same vector field. Path R2 is t comma t, and we've done this enough now that r prime of 2 is going to be just 1, 1. F of r, in this case, is going to be f of 1, 1, and thankfully here it doesn't change that much because x is 1, y is 1. All right, so we'll end up with just -1, 1. And when we take the dot product here, all right, we'll get f of r dot r prime, and I should be putting the 2's here. We're going to end up with -1 plus 1, which is 0. Okay, so the circulation f dot t ds is going to be the integral from 0 to 1 of 0 dt, which is 0. Okay, well, what's happening here is, since this is the rotation vector field, and we're looking at this line here, right, this path, it turns out that at every point along the path C, that every vector of f is perpendicular to C. So that means we have 0 circulation. Okay, now the one thing to keep in mind here, that doesn't always mean that if you have 0 circulation. 0 circulation can also mean that it's balanced. You have just as much positive circulation on part of the path as you do negative circulation on the other part of the path. All right. So let's look at this example. And this will give an example of what I was just talking about. Let's find the circulation of f equals xy, comma 1/2 x squared plus y over the ellipse x squared plus y squared over 9 equals 1. So what this ellipse looks like is in the x direction it only goes 1, but in the y it goes 3. Okay, so this is the ellipse we're talking about, and we're going to go ahead and do it counterclockwise this way. Okay, so we will travel along this path here. All right, and we're going to set this up with an r. So if you remember how we do an ellipse in vector valued functions, it's the x distance times cosine t, so that's still just 1 cosine t, then the y distance, which will be 3 sine t. And we still let t go between 0 and 2 pi. All right, now this is going to end up being kind of gross when we start working through this, but hopefully it won't be too bad. So here's our r. Now we need to find f of r. So f of r is going to be, well, f of cosine t, comma 3 sine t. Right? So what that means is we are replacing our x's with cosine t and our y's with 3 sine t. And this is what I mean when I say this is going to be kind of gross, because xy is now going to be 3 cosine t sine t. Okay. Then 1/2 x squared, well, that would be 1/2 cosine squared t, then plus y, which is 3 sine t. All right, now we need to find r prime. So r prime, well, that will be negative sine t, comma 3 cosine t. Okay, we're not done yet now. We get to take the dot product of these two. So it would be f of r dotted with r prime. Okay, so we'll multiply the first two components together to get negative 3 cosine t times sine squared t. Great, and now we're going to take these two components and multiply them together. So it's going to be a plus 1/2 times 3, so that would be 3/2 cosine cubed t, plus, now that will be 9 sine t cosine t. All right, now this is going to stretch our integration muscles a little bit, we need to take a step back to Calculus 2 and remember what we do when we have powers of sine and cosine. And when you have odd powers, that's always the nicer one because you can use the Pythagorean identity and set up a U substitution. So I'm actually going to do that by adjusting this, because this is cosine t times cosine squared t. Okay, and I'm going to rewrite the cosine squared t as 1 minus sine squared t. This is by the Pythagorean identity. Okay, and so, clean that up a little bit. And then this will be 3 sine t. Okay, now the reason we would want to do this is because now I can set up a U substitution, because if I let U be sine, du is going to be cosine. All right, so now we can set up that integral. Again, this seemed really disgusting at first, but let's see what we get here. All right, so our line integral over c of f dot t ds will be the integral from 0 to 2 pi, okay, of this monstrosity here. I'm going to simplify this a little bit because this is 1/2 minus 1/2 sine t. So these sine squared t's can come together and I would get it would be 3 cosine t. All right, then I'll get 1/2 minus 3/2 sine squared t plus 3 sine t. All right, dt. And here's where we can set up our U substitution now. So I'm going to let U be sine t, which lets du be cosine t dt. So that means this is going to become U squared, this is going to become U, and these two together are going to become du, right? Du will be cosine t dt. So you still need to know how to set up a U substitution, right? Because quick U sub is not always going to work. You could probably, if you're, I don't want to say clever, but if you're clever and masochistic enough, you can probably set up a quick U substitution here. I probably wouldn't. The only thing we need to worry about here is if U is sine t, we need to get new limits because this is limits in t. So I need new limits in U. So I'm going to get U when t is 0, sine is 0 is 0. And when t is 2 pi, sine of t is, or sine of 2 pi is 0. Oh, now that's interesting, right? Because when we get down to here, we're going to get 3 times 1/2 minus 3/2 u squared plus 3u du. But we're integrating from 0 to 0. So it actually doesn't matter what this comes out to be. This is 0, right? So the whole integral comes out to be 0. However, let's take a look at what this vector field looks like. All right, when we look at a graph of this, here's the vector field in blue, and we can see that along the path, this ellipse, the vector field is not actually perpendicular to it always. I mean, it is right here, it looks like. If we zoom in a little bit, we can see it is right here, but in these other places, not so much. Like here, if we're traveling this way, the vector field's actually pushing us along a little bit, and then eventually it's perpendicular, and then it seems to be pushing against us for a little while, and that's the key. So as you can see here, you see how the vector field is sort of a mirror image of itself? So we have just as much push with as we do against, say from this side to this side. Okay? Here, same thing. If we will have the same push with as we do against. In fact, if we just do half of the ellipse here. Well, half the ellipse would only go from 0 to pi. 0 to pi would give us the same 0 to 0 for u. Okay? So, if we did a fourth of it, okay, so if we were just to do the fourth of the circle, so that would be here, pi going from, say, 0 to pi over 2, if we were to do that, we would actually end up with the integral up here from 0 to 1. Now, I don't want to spend a whole lot of time calculating this all out over and over again, but provided I did it right, I got 3 halves. So looking at the graph again, from this point to this point, we would get 3 halves, but from this point to this point, we would get negative 3 halves. Okay, so from here to here, the circulation is 3 halves, but from here to here, it would be negative 3 halves. Then from here to here, 3 halves again. Then from here to here, negative 3 halves. Okay, so it's not so much that a zero circulation means that the path is always perpendicular. It could mean it's some situation like this guy, where it's balanced, so that however much the field or the force field pushes with you on one side of the path, it pushes against you on the other side. Okay? All right. There's a bit more I want to talk about regarding this, but I think this is a good point to put a cut in the video, so I will go ahead and do that. In the next one, we will continue this discussion and talk about the flux form of the line integral. And we will also talk about what this type of vector field actually is. One that's very nicely balanced like this, actually has a name associated with it. It's actually a very important concept in the realm of vector fields. So that's what we will tackle in part 2 of this lecture. All right, cheers.